A high wave curve with radius 900 feet is to be banked so that a car traveling at 55 miles per hour will not skid sideways even in the absence of friction. They ask us to make a free body diagram of this car and be at what angle should the curve be banked. So this question have to do with circular motion, right? Because we can see that the trajectory looks like a circle. And it also needs to do with forces because they mention about free body diagrams in here. So actually here we want to see how by analyzing the forces acting on the car can help us to understand the motion better and like even like the design of the curve. So what does it mean by the curve should be banked? What does it mean? So this is the way. This is the thing. If you got like a car like looking from the top view like this, and you see that whenever you need to make a turn, you can feel that if we travel really fast when we make a turn, we have the tendencies to be like get out the turn, right? And then there can be some like car accident, right? So we don't want to travel too much too fast. And if the road can be really like slippery, there could be some really serious accidents. So how, why so? And if you pay attention, like even in some car parking or some parking lot, when you drive down the basement, you can see that the road can be like banked a little bit. So banked means like that the surface, the road should be make some angle with the horizontal. So why do we need that? Because actually it means something. It's more for safety. So what is it? That's the purpose of this problems. It's really a realistic problem. So let's see. So in here we can see that this is a high wave curve, and we can see that the car is driving along this curve. So this curve is a part of very huge circle, and the radius of that circle is about like 900 feet. So if we convert it into meter, that it will be like around 274.3 meter. That's really huge, right? So we can see that the car travel well. I could say that pretty a kind of like a speed. It's not too slow, either not too fast, but it's not that very slow. And if we do some conversions here to meter per second, because usually we will work with in uses SI, so we should like convert everything to meter to second. So if you're not sure about the conversion, we can walk through it a little bit, just really fast, okay? So here we have like 55 miles per hour, which means it's in miles per an hour. And if we want to convert the miles into meter, which means that we need the miles to be disappeared, then we need to divide the miles with the mile, so then they can cancel each other at some point, right? And we want the meters to be here, so that's why we need some conversion factor. Conversion factor is a factor, a ratio equals to 1. So if we times them in here, it doesn't change the result, but it can help us to convert from mile to meter. Okay, and then for the hours, we just know like an hour, there will be 60 minutes, and each minute will be 60 seconds. So like an hour should be like 3,600 seconds. So then here after that we can just like cancel the unit, and that's what left each meter per second. So then we just need to do on the numerical value, times them together, divided by this one, and then we have the unit is meter per second. So 55 miles per hour will equals to 24.6 meter per second. So that's just for the unit conversion. So back to our problems here. This is the cars moving. This is the top view, and they ask us to make a free body diagram of this car. So again, what is a free body diagram? That should be a diagram that free a body, so it doesn't show any bodies here. You see, we just like represent the whole body. It's just a point mass, like as if on the mass concentrated at one point, and we want to see what are the forces that acting on it, so then we can analyze the final F net, and then from that we can find the acceleration, and then blah blah blah. So anyways, what are the forces acting on the cars here? So think about it. We know that for every object that on Earth there should be gravity, right? That pulls the object down. Then it should be like only downward towards the crowd. And the magnitude that has been studied very well, that equals to the mass times with g, and g is the acceleration, and this acceleration is specified for gravity, so it's named gravitational acceleration, and its magnitude on average is like 9.81 meter per second. We're very familiar, right? Yes, this one varies between positions on Earth, but on average we take it like 9.81, the very most common one. And sometimes for like problems when they don't focus too much on the precisions of the value, they can just take it like 10. Okay, so if you just came across sometime like, oh, why is that 10m, so that's 10 is like that from the g. Okay, so anyway, that's also a very like fast summary revisions of the weight. That's on way the force acting on a mass on Earth. What other forces that may act on the car? Well, in order to answer these questions, this is a tip. Think about which other body that touching the object, the car right now, because touches mean here that they are in interaction with the car, which means that it will exert some force on the car. So the car is driven on a highway, so should it be the highway? And the highway here is being banked a little bit, like we have mentioned before. So think without a highway, then the car, if just under the exertion of the gravity, it just like go down to the core of the Earth, right? But in fact, here it stay on the highway, which means that the highway should add some force that against the influence of the gravity. So it means it should be in the opposite direction. Okay, and actually in this case we also define the normal force. Normal force, just by its names, means that it will be normal, and normal also means that perpendicular to the surface of the contact. So that's the contact surface here, and the surface is actually the highway. So if we look at them sideways, this should be the highway, right? This is the highway being banked, and you can see that it's perpendicular to this one. That's why this should be the direction of the normal force, right? Is there any other object that in direct contact with the car in this case? I don't think so, right? They didn't mention about like the air resistance here, so we can just ignore it. It's like negligible. So basically, there's just like two forces: the normal force, normal to the highway, and the weight that normal to the crowd and downward. So if you got these two, then you got the full point for this one. Okay, so then we done making the free body diagram of this car. So in this case, the problem has been simplified that in the absence of friction. Okay, so what if we also have friction? Then in that case we have to apply the friction. Actually it will be against the motion, and we can see that for the cars here, it would have the tendency to like go down this way, right? Because the component of weight along the incline like this one would have the tendency to move the car down this way. So then friction, if there's some friction, then it should like goes up, right, against the motion like this, right? That's in case that we have friction, but in here we don't have friction, so maybe just ignore it for now to make the problems more simplified for us to solve for the next question. Okay,